Good morning. I'm here with Jake VanderPlas.
That's right.
Is there like a...
I'm sure there's an original Dutch pronunciation, but it's been lost over the generations.
And the Dutch vowel system is just like wild, untamed territory, for me at least, anyway. There are a lot of vowels. And you are like a major figure, at least in the data science space. So folks may know you as the author of the Python Data Science Handbook. You're a scikit-learn contributor.
Well, I'm an emeritus contributor.
Emeritus contributor, okay. Yeah. But people have probably used code that you wrote if they're Python folks. You work on Vega, Altair. I'm sure I'm like probably a bunch of like astronomy stuff.
Yeah, AstroPy. I've done a lot of work there.
And you were for a long time at UW, which is also where I got my degree. We're in the same office, obviously. Yeah. And you're on the Colab team now. So
that's right. Yeah, Google Colab.
All over the space. So I'm Rachel from Kaggle. And I have coffee. And I see you don't have coffee. That's fine.
No, I've already had 2 coffees today, though. So
good job. Yeah, so I thought it would be helpful. Just like it's nice for me to catch up with people, and then also it's like we record it and then share it with other folks. I think it might be helpful for people to hear a little bit about sort of your journey and how you got into data science. But I'm also really interested in how you got involved in the open source and FOSS. Would you call yourself a FOSS person?
Yeah. So I've done a lot in that area. So
how did you get involved?
Yeah, so I started programming when I went to grad school in about 2006. Started on Python then. I'd done a little bit of C++ before that, but hadn't really coded for like 5 years before joining. Actually, for like 8 years before going to grad school. So I picked up Python because there was, astronomy at the time. Most people were using this language called IDL. Which I don't know if you've come across. No. It's a proprietary language that's sort of like a dynamic wrapper around Fortran that's used in a number of sciences. And the first research advisor I worked with recommended that I try out Python. He said, Python's the future. Everyone's going to be using it. And luckily it turned out he was right. So I was the lone grad student using Python, where everyone else. A few other people were using Python, but for the most part, people were using IDL. And it turned out that that was the way that the astronomy community was heading for various reasons. So it set me up pretty well to start contributing to a lot of the core tools behind kind of the astronomy data processing stack. And so my first real foray into open source was after my first astronomy paper in 2009, my first author paper. I had all this code that I had written, and it was basically a manifold learning pipeline designed for astronomy data. And for that paper, I essentially spent an entire summer re-implementing this algorithm that I was reading about in an applied math paper. And in the applied math paper, they had kind of a prototype implementation in MATLAB, but we found that it wasn't fast enough for the size of data that we needed. So I spent a lot of time, actually I wrote a lot of C++ wrapped in Python to make this implementation fast enough. And at the end of it, I kind of did the typical thing and put a tarball on the website, link to it in the paper. And I thought to myself, like, this is absurd, because the next, if anyone wants to do anything with this algorithm after this, they're going to have to go through the same exercise I did, or download my tarball, which I was not very proud of. It was kind of this mishmash of C++ and Python. So I extracted out some of the code into a lot of it was reliant on this ball tree data structure, which was a data structure for fast nearest neighbors queries in high dimensions. Okay. And I emailed the SciPy mailing list, and said, hey, I have this code. Do you think this is going to be, this would be useful in SciPy? Thinking like maybe I could contribute to the community. And it was like crickets. I didn't hear from anyone. And knowing now, like, having followed this SciPy mailing list for a decade, I know that I was, that's not the kind of email that gets answered. Just no. But fortunately, there were some folks starting this project called Scikit-learn at the time, and they were looking for contributors. And one of the folks emailed me and said, "Hey, your code might fit in Scikit-learn." So that turned into my first contribution to Scikit-learn, this Balltree code, and it's now on, I think, the 4th or 5th generation, and every line of code that I initially contributed has been wiped off the planet, thankfully, for Scikit-learn users. But yeah, so that was my initial foray into machine learning. Was writing these kind of data structures to make fast versions of these machine learning algorithms. And I sort of it was really amazing because I'd never had any formal computer science training, and just the process of contributing code to Scikit-learn and working with people like Gaël Varacou and Olivier Grizel and some of the others who were there early on. I learned so much from them just by having them review my code, and it was brutal at first, but I kind of worked through it, and through all that I learned how to. I wasn't even using version control before. I learned how to do Git. I learned
trial by fire.
Yeah, testing, unit testing, things like this, and I owe so much to them, to that Scikit-learn team, for kind of holding my hand and helping me through all that. And then eventually I sort of got hooked on it. I started seeing more places where I could contribute to Scikit-learn and add some fast algorithms to underpin different things that I wanted to use in astronomy. And then my real my first step into the actual Python community was a few years later in 2012. There was this PyData meetup that happened at Google Mountain View.
Was that the first PyData?
In the spring of 2012, yeah.
Oh, wow.
And they invited Olivier Grizel to talk about Scikit-learn. And he said, "Well, I'm in France, I can't go, but there's this guy Jake who's on the West Coast." And he put me in touch with the PyData organizers, and they invited me in his place to come talk about Scikit-learn. And I was like totally out of my league because I knew nothing about machine learning except these.
You know nothing about it, but you've implemented some stuff.
Yeah, I implemented the data structures to make some of the algorithms fast, but as far as giving a general overview of machine learning, I felt so out of my league. So I kind of it was pretty ridiculous. I just brushed up on whatever I could and kind of read everything I could for a few weeks, and then tried to stitch together a basic intro to Scikit-learn and machine learning. And I put together this 45-minute thing, which I'm sure you can find the video somewhere online. But the interesting thing was that at that meeting, I met all these people, all these people who had just been kind of figureheads and names on mailing lists and package author lists. And all of a sudden I'm standing there meeting Travis Oliphant and Fernando Perez and all these people who were who loomed large in my mind. And it turned out they're just really nice people. And one thing that happened at that meeting is after the tutorial, Fernando came up to me and he's like, "Hey, I want to show you something. I took all your tutorial content and I translated it into this thing called the IPython notebook." He's like, "And all you have to do is open this notebook and then you can execute it right on there." And I was hooked from the IPython notebook had been released 7 weeks earlier or something like that. So it was brand new. And that's what Fernando and Brian were talking about that day. So that was that's how I got, and again, I just totally got hooked, being able to chat with these folks who had implemented all these packages that I'd been using for the last 5 or 6 years in my own research. It was just incredible, So in the meantime, I had contributed a lot to SciPy because things in Scikit-learn, some of these algorithms in Scikit-learn sort of made sense more upstream in SciPy, and I had started releasing a lot of astronomy-specific open source code and things like that. And I totally I managed to finish my PhD, but only because my advisor was very forgiving and sort of was willing to look at all my code contributions as something that contributed to the PhD. And so so by that time I was firmly on the path to becoming a software engineer and no longer doing much in the way of research. And that's been so that was 2012 that I got my PhD, and in the 7 years since then, I've continued on that path and slowly kind of did more and more software engineering in academia, in support of research, and then eventually in support of other people's research, and then eventually just because I liked building tools. And after a while, it seemed like I should go somewhere where I could learn more about software engineering, and that place turned out to be Google.
Yeah, and it's interesting thinking about like who's doing open source, because it is a lot of academics, but at least in the US, and certainly in my discipline, which is linguistics, like software authorship is not really considered like something you can like make the top line item in your tenure packet.
It's true, and it's unfortunate, and that's changing a little bit. There are more and more positions, at least in the astronomy world, that are recognizing the importance of software and software contributions, but it's still, I think, there's a lot of inertia in academia, and I'm not sure I could have gone on in the tenure track in astronomy without kind of setting some of that software work aside and working more on beefing up my more typical academic resume. And I published plenty of papers along the way, but they're not near enough to be kind of like competitive for an R1 tenure track position. And so it's kind of slowly coming to the realization that I'm a software engineer, not a researcher, but I can write tools that support people's research, and that's something that really is fun for me.
Huh. Something that I know about astronomy as sort of a field is that I sort of think of it as like the original big data field, because y'all have like a lot of data. So,
I don't know if you saw what this black hole discovery.
Yes, I've been reading about it.
There were pictures of some of the researchers involved standing with their stacks of terabyte hard drives with all the data on it, and they literally the data was to the point where it was not cost effective to send it over the internet, so they literally flew with hard drives or shipped hard drives around the world in order to gather the data into one place.
So coming from a very large data set background, do you have any good pointers for people who are maybe used to working with smaller data sets? What are sort of the big mental shifts you have to make where okay, I can't do X, I have to start doing Y now?
Yes, there's obviously different types of big data, right? There's the big data where relationships between every byte in your data set matter, and you need to process the whole thing as a whole. It turned out most of the kind of big data that I dealt with in my own research was stuff that lent itself well to massive parallelization. So imagine you are looking at one star and you want to analyze that and find some sort of frequency of oscillation or something like that. And that's easy. You can do it on your computer. But then you want to look at a billion stars and do the same thing for every star. And in my case, just finding a way to kind of farm out those jobs where each one might take 5 minutes of CPU power, but you have to do that a billion times. You can't do that locally. That sort of thing was what I encountered most often, and what I ended up using was I was often cloud resources, using the best tool back then was Star Cluster to run multiple jobs on AWS, and so I ended up using this tool called Star Cluster with some AWS cloud time and kind of running all the things in parallel. It gets much harder if you have something like this black hole. This black hole study recently, they actually had to do cross correlations between all the data.
Oh, wow.
So they needed, I haven't actually looked into the details of it, but I know that the types of computations they were doing were really, really sophisticated, and they needed like big, large machines that could hold large portions of the data set in one place at the same time. And, you know, that's something that I personally don't have as much experience with. But yeah, the cool thing about doing these sort of massively parallel exercises is there's a lot of tools out there that are built and can help you kind of farm out these when you want to run a lot of jobs in parallel.
And it sounds like you moved off of, well, so you said you already had the background in C++, which in the R community as well, a lot of very optimized packages are wrappers over C++. So it sounds like you pretty much from the beginning were using Python and C++ together. Is that still?
Yeah, I dropped C++ and started using C, and then started using Cytheon. Have you ever used Cytheon?
I haven't heard of it. I've heard of it, but I haven't used it.
So Cytheon is awesome. It's like this hybrid child of Python and C, and the way it's actually one of my favorite programming languages to write in, because you can literally just write Python code and compile it. But if you need a little bit of speed, you know, if you need to speed up one of these inner loops where there's a lot of Python overhead, you can add some kind of simple C style annotations, and then it'll compile to more efficient code.
I think I saw a PyData talk about this at Redmond's. This is the last time it was in Seattle.
Yeah, so the Cytheon is really cool because so a lot of the stuff after that first contribution, I talked about the C++ ball tree. The second round on that was a Cytheon version of the ball tree. So dropping a lot of the C++ cruft, making a little bit more, a little bit easier to maintain, and then so Cytheon is kind of the way I've gone since then.
Yeah, interesting.
And I haven't written any C++ for about 10 years now, and I know the language has evolved a lot. So I tried to read someone's C++ code a few weeks ago, and it was like, this is a new language. It's completely different.
Yeah, it's not an area of my specialization. Pointers. I just don't want to deal with pointers. I don't want to move them. I don't want to think about them.
Yeah, the memory management stuff is, it's a pain.
Yes. I mean, it's better than what R does, for sure.
Yeah.
Which is allocate like contingent, like congruent chunks, but.
But at least it takes care of it for you, right?
Yes, that's the thing. Like I'm willing to trade off a little bit of processing speed for a lot of convenience, and that's just like where I am right now. But also, I'm mainly working with text data these days, and it's just not that big.
Yeah.
Like even a lot of text data is not that much like space on a hard drive. So.
Yeah. Cool.
So so what are sort of like open sourcey things you working on these days? Yeah,
my big open source contribution these days is the Altair package, which is essentially a Python wrapper for the Vega Lite visualization grammar. The idea there is that Vega Lite gives you a way to specify everything you need to create a chart within a compact JSON structure. So you basically say, like, I want the x-axis to map to this data column, the y-axis to map to this data column, the color to map to this data column. And then you can specify kind of like the color scheme and how it's determined. And it ends up being a really compact declarative specification that can then be rendered by this JavaScript backend. And so what the Python tool does is give you a way to create these specs without having to edit JSON by hand, which
ideal.
And it's been a really fun project because it's building on some really cool work by the UW Interactive Data Lab with these Vega and Vega Lite's schemas, and it kind of scratches the itch that I've had for a while, which is to have some way of plotting things in Python that makes more sense than a lot of the imperative tools out there.
Yeah.
You know, kind of the standard in the Python world is matplotlib, which is built from. It was kind of built 10 or 15 years ago to mimic MATLAB.
Yep. That wonderful visualization language.
Yeah, it's and it's really powerful. You can do almost anything in it, but it takes a lot of tweaking because a lot of the things are very imperative. You have to specify kind of everything yourself.
It feels like driving, but instead of using like pedals and like a steering wheel, you are in the engine, like moving the cars that you need to move. That's how it feels to me. It's just like so low level, very powerful, but very low level. Yeah.
So the Matplotlib, I should say, I use Matplotlib for basically every paper that I've ever written, and I couldn't have done my PhD without it. And I've contributed to Matplotlib, but there are these itches it doesn't scratch for me. You know, the declarative specification,
and like also very high level
declarative specification, and also interactivity and kind of web first visualization and stuff like that.
Yeah, absolutely.
So Altair has been a really fun project to work on because it lets me think about the fun things like the APIs and how I, as a data scientist, want to interact with the code and the data. Fortunately, all the things that are hard to me, like how to make JavaScript implement this visualization, are taken care of by the experts. So I don't have to think about that.
That's nice. Just distribution of labor, I guess like a normal developer.
Yeah.
Like normal data scientist. You're not going to write everything from scratch yourself.
Yeah, and we're with Altair, we're about sometime by the end of the week, I'm hoping to release Altair 3, which is a big improvement over what we've had available for the last year.
Yeah, I think last time I talked to you about it, you'd just done like a subversion of 2.
Yeah, I'd done a couple of. I think we've done up to 2.4, 2.5, but yeah, 3 is going to be this big jump that implements a lot of things like compound marks, error bars, and box plots. A lot more flexibility around tooltips, a lot more flexibility around wrapped facets, and so instead of having 10 charts on a big line, you can have them kind of like
like the way that you would want it to be. Yeah.
So things like that. I think it's going to be a really good enhancement to the tool.
Yeah, no, it sounds like it'll be much better. Definitely coming from so I'm sure you know this, but in R, plot is just one of the base commands that comes with the language. Like it's such a central thing. And then coming to the R like visualization ecosystem, it was like, you know that GIF with a guy from Community who comes in with a pizza box and like everything's on fire? Yeah. Which is like, oh my gosh, there's so much and it's so different and there's so much going on. I have used Altair. I like it. I don't know. My heart belongs to ggplot too. But so is there anything in particular you want to share with the Kaggle community before we wrap up?
Well, I just a couple months ago put a Kaggle renderer for Altair.
That's right.
Into the package. So you can now. It was a little bit hokey to use Altair within Kaggle a while ago, but now it's pretty straightforward.
Yeah, there's still that HTML widgets bug, but I don't know that's ever gonna get fixed.
Oh, really?
Yeah, have you run into it? Sometimes an HTML widget will be rendered like by a 1 pixel by 1 pixel.
No, I haven't seen that.
It's a known bug. I know that the team's not focusing on it. I'm not a front end person. Like I don't think I can fix it. But yeah. But it doesn't happen with Altair anymore, so you can get your nice syntax visualization.
We're good to go.
Yeah, absolutely. All right. Well, thanks so much for joining me.
You're welcome.
It's good to talk to you. And so we're filming this before PyCon, but it will air after PyCon. So check out, you have a PyCon talk, right?
Yeah, I'm talking about visualization at PyCon. So.
Fancy that. And I'm talking about when not to do deep learning, which is
cool.
Much of the time. That's a spoiler alert.
Yeah.
It's not. There's a small set of situations where I personally would use deep learning.
It turns out Gaussian naive Bayes works pretty well most of the time.
Yeah, absolutely. You got lots of options.
Yeah.
All right.
Cool.
Thanks for joining.